In this lecture, we're going to be talking about single-phase inverters with resistive loads. So I've gone ahead and drawn the circuit for this inverter here on the left. So as you can see, we have transistors Q1 through Q4, then the input voltage, and a resistive load at the output. So this is the simplest type of inverter there is, because not only is it single phase, but the load is also only resistive. And so we're going to begin talking about inverters by taking a look at this inverter configuration, because it's the simplest type. So remember that what we're trying to do with an inverter is to make an alternating voltage at the output using a DC voltage at the input. So what we need to do is we need to find a way for us to alternate the input voltage with respect to the output, such that we can get both a positive and a negative voltage at the output. And again, using a positive voltage at the input. And so the reason why the circuit looks like this is because what we're going to do is we're going to alternate switching of transistors Q1 through Q4 to achieve that. So let's go ahead and see how we can do that. So in this circuit, for example, if we say that we're going to switch Q1 and Q4 on while leaving Q2 and Q3 off, then the circuit would look like this. You would have Vn connected through Q1, through the output load, through Q4, and then back to the input. And so what you can see here is that we've connected the positive terminal of Vin to the positive terminal of Vout. And likewise, we've connected the negative terminal of Vin to the negative terminal of Vout. So let's go ahead and write this down. We're going to say that if Q1 and Q4 are on, then Vout is going to be equal to Vn. Right, because we've connected positive to positive and negative to negative. So now we need to find a way to invert the polarity of the input voltage with respect to the output voltage. So what we can do is we can switch in the opposite transistors for that. So instead of switching Q1 and Q4 on, we're going to say that we're going to switch Q2 and Q3 on. So if that's the case, then the circuit will look like this. We're going to have Vn connected through Q3 to the output load, through Q2, and then back to the input voltage. So you can see here that we've connected the positive terminal of Vn to the negative terminal of Vout. And we've connected the negative terminal of Vn to the positive terminal of Vout. So essentially we're reversing the polarity of Vn with respect to Vout. So we're going to say then that if Q2 and Q3 are on, then Vout is going to be equal to minus Vn. And of course, for these two states, I'm assuming that the opposite transistors are off. So when I say that Q1 and Q4 are on, I'm assuming that Q2 and Q3 are going to be off. So now if we do this, and let's say that we switch Q1 and Q4 on for the first half of the cycle, and then we switch Q2 and Q3 on for the other half of the cycle, then the output voltage would look like this. And this, of course, we're going to repeat every cycle. So this is going to repeat after 2 pi, and it's going to be like that previous to the origin here. So we've made an alternating voltage at the output with the DC voltage input. But as you can see, this is nothing close to a sine wave. It's basically a square wave. So it's an alternating voltage, but it's going to be very, very distorted. Because remember that we're trying to achieve a perfect sine wave at the output. So this is not very close to being a sine wave. However, what we can do is we can make one more state. Now let's say that instead of switching the diagonal transistors, so Q1 and Q4 and Q2 and Q3, we're going to switch either the top 2 transistors or the bottom 2 transistors. So let's see what happens. Let's say that if we switch Q1 and Q3 on, for example, then what would the output voltage look like? So the output voltage for that case will look like this. We're going to have Q1 connected through Q3 to the output load, and then back to Q1. So as you can see, the output load is basically short-circuited because we've turned on transistors Q1 and Q3. So we're connecting the positive terminal of Vout to the negative terminal of Vout. So Vout essentially is 0. right? Because there's no potential difference between the positive and the negative terminal. They're basically connected to each other. So the output voltage must be 0. So we're going to say then that if Q1 and Q3 are on, then Vout is going to be 0. Now we can do the same thing by switching the bottom 2 transistors. So if we switch Q2 and Q4 on, then the output voltage will be short-circuited through those 2 transistors. So if Q2 and Q4 are on, then Vout is also 0. So what would the output voltage look like now? Now I'm going to define one more point here. I'm going to call this point right here delta. So then this point right here would be pi minus delta. This point right here would be pi plus delta. And this point right here would be 2 pi minus delta. And so the reason I've done that is because we're going to say that from 0 to delta, we're going to make the output voltage 0. So we're either going to switch Q1 and Q3 on, or we're going to switch Q2 and Q4 on. Essentially, we want to make the output voltage equal to 0. So then the output voltage here would look like this. It would be 0. Then we're going to switch Q1 and Q4 on. So the output voltage is going to be the same as the input voltage. Then back to 0. And from pi minus delta to pi, we're going to switch again the top 2 transistors on. So it's going to be 0 again. And then we're actually going to alternate from pi until pi plus delta. We're going to switch the bottom 2 transistors on. So the output voltage is still going to be 0, but we're achieving that by switching now the bottom 2 transistors. And then after that, we're going to switch Q2 and Q3 on. So it's going to be minus Vin. And then we're going to do again Q2 and Q4 on. So now the output voltage looks a little bit better. It's resembling more a sine wave now, because we've essentially added one more step in the output voltage. And so if you were to do a kind of Fourier analysis on these 2 waveforms, either the top one or the bottom one, you would see that the bottom one is less distorted. So the bottom one essentially resembles more a sine wave than the top one. And so this is a common switching scheme that is used in some inverters to achieve sort of a sine wave at the output. And of course, on these 2 waveforms, this point right here would be Vn. This point right here would be minus Vn. And likewise here at the bottom, this point right here would be Vn. This point right here would be minus Vn. And then I'm going to go ahead and write down the transistors that are being on during each state. So here we said that Q1 and Q4 are on. Here we said that Q2 and Q3 were on. Likewise here, Q1, Q4, here Q2, Q3, and then here we're going to say that we're going to do the top 2 transistors, so Q1 and Q3. Likewise for this portion only, Q1 and Q3. Now for this portion, it's going to be Q2 and Q4, and same for this part right here. And so notice the pattern here. We're switching Q1, Q3 on, then Q1, Q4, then Q1, Q3 again, then Q2, Q4, then Q2, Q3, and then Q2, Q4 again. So one thing that's important to note here is that we have 2 ways of making a 0 voltage at the output. Again, we can either do Q1 and Q3 or Q2 and Q4. However, it's important that we alternate between those 2 combinations, because every time we switch a transistor on, we're putting some stress on the transistor. And so for that reason, it's important that even though we have 2 ways of making a 0 voltage at the output, it's important that we alternate the way that we do it to distribute the stress between all the transistors equally. Now, as far as the output current, I'm not going to draw it because since we have a resistive load, then the output current is going to be just like the output voltage, except that it's going to be scaled by the output resistance. So in other words, Iout is going to be of the same shape as Vout that we've drawn here, but it's going to be Vout over R essentially. But again, this is the simplest type of inverter as a single phase with a resistive load. And we've seen how we can use these 4 transistors to achieve an alternating voltage at the output. That's still very distorted, but it's kind of closely resembling now a sine wave.